Okay, so previously we have derived different scheme, modulation scheme and demodulation scheme, or detection for ASK, BPSK or QPSK, and FSK also, FSK. So all this modulation scheme was coherent detection. So what was a coherent detection? In coherent demodulation or in coherent detection, there is a local reference signal. For example, if I divide in two-part transmitter, for example, you have a baseband signal, means your low frequency. The frequency is up converted by kind of carrier, right? Cos 2 pi fct. So, for example, this is a message signal MT, for example. So, this signal is now up converted by FC, depending on what kind of modulation you are using, right? Now, after up conversion, whatever happens, we are actually more interested to the receiver. So, for example, this is our XT signal. XT signal. In receiver side, in YT, when you receive the signal, we will down convert the signal, right? That has to be done. We will use the same carrier we used here. So cos 2 pi fc t. So this is actually very like fundamental stuff. So here you see the carrier we use to up convert, same carrier we'll be using for down conversion. Means actually the receiver side have a knowledge of the carrier of the transmitter side. That's why it's called coherent, because it inherits the knowledge of the carrier signal. This one. Okay. So a local reference signal at the receiver which has a knowledge of the phase and frequency of the carrier. Now here, when we usually up convert a signal, we do not add a phase here. We do not add a phase. We do not add. While in the channel for transmission, this phase is actually added in the system because of the noise process. We in most of our scheme, we do not actually consider this one. We only consider what? Additive white Gaussian noise, right? In the channel ANT. So why we didn't do that? Why we didn't consider any phase in the system? Because this phase, whatever the phase will be there, they are estimated in the channel estimation by different technique. Okay, this phase actually is added here, so that if some signal in YT, there is a, for example, phase is introduced, which is a noise process function of t, that signal will phase will be actually will be cancelled out by the knowledge in the receiver. So in the receiver receiver always do an estimation of the channel. It actually predicts what kind of channel the signal is passing through. That's why actually probably you have seen in all our coherent signal, we never used phase in our signal, in our receive signal, because that is actually cancelled out because of the estimation or knowledge of the phase in the system. That's why that is called a coherent detection or coherent demodulation in the system. So far we have studied everything, they are actually coherent. Now you can see from the mechanism itself that if a receiver has to have a knowledge of the channel or the noise process in the channel as well as the carrier, the receiver itself will be complex, because it has to always estimate what kind of noise is adding in the system process. So it has to monitor the system. So this receiver is complex. So there is a alternative way, non-coherent. What is non-coherent? Non-coherent means this knowledge of this part, the receiver do not have any knowledge of this part. It do not do this operation. Okay. So question is, if it do not do this operation, there we need a local reference, right? How it knows this reference signal? Isn't it, guys? That's the question. For example, I give you an parametric value. For example, our message signal, which is in kilohertz. For example, my voice signal is actually 30 to 300 kilohertz. For example, 300 kilohertz signal. This signal cannot be go. I mean, it's a very low frequency. So what we do, we actually modulate with a high frequency. For example, this FC is 1 megahertz. For example, 1 megahertz signal. So now the signal it goes, it's actually 1 megahertz modulated signal, 1 megahertz signal. When we receive a signal, that is also a 1 megahertz signal, high frequency signal. So what we will do, we will actually try to put a reference signal like in coherent is close to 1 megahertz, same to this one. Actually, it's 1 megahertz plus so 1.3 megahertz. Actually, it's supposed to be 1.3. Okay, so it will be 1.3 megahertz. So you receive also 1.3 megahertz. You have a 1 megahertz signal. So that after down conversion, you have 300 kilohertz signal. You can retrieve. So this signal, if in the receiver, if we do not have the knowledge of this 1 megahertz, how I know that how to down convert this signal? Because this signal is 1.3 megahertz. My information is 300 kilohertz in the it's actually in the within this high frequency. So I need a reference signal so that we can down convert it. If you do not use a reference signal anymore, for example, you do not have a knowledge of this one, there is no connection. Okay, so how to do that one? That's the question, right? Obviously you need a signal to be down converted. So what would be that signal? Okay, let's see. So in non-coherent demolition, it do not need a local reference. Actually, it need a local reference, but this local reference is not synchronous with the in the transmitted signal. So knowledge of the phase of the carrier is not available. So now this guy, so in new system, for example, you have a Y. Transmitter is same. Transmitter for coherent and non-coherent is same always. Only difference happens in the YT. Here there is a, of course it has a reference signal definitely, but this reference signal have nothing to do with the transmitted carrier. It cannot keep track. Okay, so the knowledge of the phase of the carrier is not available. So there is no knowledge of the phase here. Previously this phase knowledge was here, this phase knowledge, so that phases in the introduced in the channel can be encountered. But here this guy, he can only have a frequency. He can use a frequency to down convert it. He cannot have a phase because he do not knows it, right? Okay, so what will happen in channel? The signal will be received in the channel. So then the down converted signal, so this signal YT will automatically will have a phase noise, and also this signal will also have a phase noise, Fn for example. It is not cancelled out anymore. In our coherent detection, there is no phase noise here because it's cancelled out by this one, knowledge of this one. It can be subtracted because it's estimated. Noise is you cannot exactly know the noise, but it can estimate the value of the noise, right? Because this is a random signal, random process. So in non-coherent, two things happening. The reference signal have no knowledge of the carrier. So this F will be somehow you have to know it. He have to know, the reference signal have to know which frequency it will generated, and there will be no phase noise. So automatically phase will be added in the system. Means what? This system is more noisy, poor performance, poor bit order performance, because it cannot cancel out this one. This remains. So noise performance is worse than the coherent receiver definitely, and the structure of the receiver is simple. You see, it looks like simple, because these do not have this stuff for estimation. Of course, this process is faster, but it cannot give you very better performance in the system. That's actually the difference between the coherence and non-coherent system. So actually there is a pros and cons. If your system is very sophisticated, you will have you will be using a coherent system. But for example, if your system is not that much sophisticated and you do not want much complexity, so non-coherence. Now question is, okay, question is, if this reference signal do not have a knowledge of the carrier, how or at what frequency he will generate this reference signal? Isn't it the question, guys? Definitely I need it, right? In a transmission, whenever I have a signal, I want to down convert it. What question is, what will be this signal if no pre-knowledge reference signal is used? The answer is previous bit. What does it mean? Previous bit means actually you will delay your own received signal, and that signal you will uh, be using. For example, giving you an example. So, for example, how much was our signal previously? 1.3 megahertz. Megahertz. Okay, signal will be fluctuating, plus minus. It will be fluctuating, varying within few kilohertz range. So what you will be doing that, okay, by engineering, you will actually make a delay. How much delay? It depends. Typically, the pulse, each the next previous bit, the signal comes here. Let me draw it a little bit a different way. It will be better to see. Whatever signal you have, you will delay that one. That signal will be. So you see, this is also same multiplexer. Sorry, mixture. So whatever signal you have, YT, for example, it will be delay in one pulse, and that pulse will be, this will be as a reference signal. Reference signal. So you have a YT signal, and YT signal have 1.3, for example, in our previous cases, megahertz, for example, which actually, because for example, my voice is modulating, right? My modulating voice is fluctuating. So previous bit will not be the same. Like two successive bit can be same, two successive bit may not be the same. Okay, so that's all. Then the next is the same as the typical coherence detection system. You have an integrator, then you send it to the sampler. From the sampler, you go to the decision circuit, right? Detection or decision circuit. This is a T sampling. You see how the receiver becomes very simple. Okay, let's see with an example. For example, transmitted. Okay, so let's do it for a specific scheme. So this is a non-coherent for BPSK. Okay, so we will do this scheme for BPSK. So in BPSK, for example, what is our typical transmitted signal? XT. So this is our for XT signal is expressed as A0 PT. We know for BPSK binary. So A0 belongs to two cases. Case will be minus A plus A. So plus A will be represented by 0, minus A will be represented by 1. So this is actually our transmitters. For example, if I see in constellation, so this will be 0, this will be 1. So this is plus A, this is minus A. So this will be bit 0, this will be bit 1. Okay, this is transmitted signal. In transmitted signal, the XT will be expressed as what? The 0 will be expressed as, we did it many times, so I'm writing it directly, twice EB by T cos twice by FC. Of course, T is 0 to capital T, and 1 is twice EB by T minus, this minus. So this is a transmitted signal. So how the signal will be received? The signal will be received as a YT. Okay. So we can use, most likely we will be using a BPS bandpass filter to eliminate any kind of noise we receive. Then it goes to a mixture for down conversion. How we down convert? Because we do not have any reference signal. So what we will do, we will take a delay of T. That delay will be added. So this is done converted. Now the as usual process, it will be integrated 0 to 3, goes to a sampler of T and goes to a, which will be the RT, and it's a detection. So if is the case, now we are saying that in, because it's a non-coherent system, so just for make of simplicity, we are assuming that we are not considering the additive white Gaussian noise. We are actually will consider the noise which will actually most hamper our system, which is actually the phase. So a phase will be introduced. So in YT, what will be the receive signal for this corresponding receive signal? Okay, for 0, for example, for 0, what will be our receive signal? Twice EB by T plus theta. Now this theta is introduced here. For 1, it will be minus. So you see, this is the difference between the coherent and non-coherent system. In coherent system, this theta never arises because we have the knowledge. That's why in detection system, in down conversion system, we use the phase in the carrier, so that got eliminated. But here we do not have any knowledge. Okay, so what we are assuming that only phase. So in receiver only phase noise introduced. Okay, so this is for one for bit 0, another for bit 1. Now here we'll actually more concentrated here, that okay, whatever signal comes, it can happen, for example, in BPSK binary, yeah. So it can be 1 and 0. For example, here it can be 1, the next delay it can be 1 or 0, right? So actually you see there are two cases can arise here. Okay, so case 1, let's see what happened in this down conversion system. In case 1, we say A0 is equal to A0 minus 1 here. Means actually the A0 bit, for example, you are in YT, A0 is there, A0 signal is there. So we say this is A0 and A0, the previous bit, they are actually the same. So what we are saying that, okay, the present bit same as previous bit. So there are two, what kind of possibilities could be? When 1 was here, like the value of A0 is 1, after delay, that value also be 1. It can be 0, it can be 0, it can be 0, 1. So the 4 combination, it can be 0. So present bit is 0, previous bit is 0. Present bit, so this is present, and so it passed, say passed previous bit. So it can be 0, 0, it can be 1, 1, it can be 0, 1, it can be 1, 0. I'm writing it separately to distinguish that, okay, same bit is transmitted. A0 and A0 minus 1 means previous bit was same. Even if it's 1, then it's also same. what happens if they are the same? See what is our equation comes. Okay, so y0 for 0, for example, for 0, this signal EB, this signal EB will be here. So next bit is also 0, 0. So this is 0 bit, this is 0 bit, because they are same, case 1. So 0 is actually this equation. What will happen to this equation? Just to like what will happen if yt and we say yt minus t, previous bit, this one is yt. So this is a yt, this is a yt, this one we can say y t minus t, previous 1 bit delayed bit. If they are 0 0, what will happen? So this signal itself will multiply with itself, isn't it? So RT. So this is RT signal. RT. So what will be the RT? This signal is multiplied with itself, right? So it will be twice EB by T and cos square, right? Cos square twice pi FC T plus theta dt. So after this integrator, what will happen? So we will be 0 to T. So twice EB by T, not twice EB. Let's make it EB by T. 2 comes here. So 2 cos square theta is 1 plus cos twice theta. So 1 plus cos twice pi FC T plus theta. Right? dt. 0 to T. Now, if you make the solution, what happens? EB by T. So 1 will be T cos square. This whole term will be 0. We have seen it in our earlier evaluation. So T cross. So it is actually EB. Means if the same bit is here is 0 0, then we will have EB. Now see if it is different. 1 1. What will happen? This minus, this signal actually goes. So this signal will multiply by with itself. So minus will be plus. So actually the signal will be the same. If it's 0 0 or 0 1, still the output will be EB. So let's summarize. So if yt equal to 0, yt minus t is 0, RT equal to EB. Also, yt equal to 1, yt minus t equal to 1, they are same. There also RT becomes EB. So case 2 is they are not same. Case 2, second case, if they are different. What? So A0 is not same as previous bit. It's complement of the, means actually present bit is not same. Present it is not same as previous. So here, for example, if it's 1, that is 0, previous bit be 0, 1 0 or 0 1, whatever. So if it's 1 0 or 0 1, what will happen? 1 and 0 means this 1 0 will multiply with 1. Everything will be same except here is a plus, that here is a minus. Plus minus minus. So actually it will be nothing but the, so RT will nothing but the minus EB, isn't it? Previously it will be plus, now it will be minus, isn't it? Even it's opposite, the same thing. If it's this becomes 0, If this becomes 1, this will be still the same, minus EB. So if they are complement, the output is minus EB. If they are same, they are plus EB. So let's summarize this. So what is our decision then? So what is our decision? Our decision that, okay, if RT is greater than 0, greater than 0 means actually EB. Okay, RT is greater than 0, some positive value, what will be detected? EB, what will be detected? Now we will actually here make a table. So 0, 0 and 1, 1, or 0, 1, 1, 0. What happens when the same bit is transmitted and detected, present and previous is same? We received 0. EB plus positive value. You see what was our transmitted signal? This one. A is 0, minus A is 1. So EB is corresponds to 0. So RT is greater than 0, detects 0, less than 0, detects 1. That's actually our summary from this decision. So if this is the case, then 0, 0 or same bit, previous bit gives us 0. Same bit and previous is not same, it gives us 1. 1 means actually negative value. You see, 1 is the negative value, and negative means negative EB. What is that? Case 2. Yeah, this one. So what kind of which which gate gives us this expression? What is the expression for this truth table, for example? Guys, which truth table is gives us this characteristics? If it's same bit, you get 0. If it's different bit, you get 1.
Sir,
Mm.
sorry.
So which truth table gives us this characteristics?
Sir, XOR.
This gives us actually XOR gate. So means actually in our receiver there must be an XOR. That's actually the idea. That's why we did all these things to get the idea that how to implement this mm, delay stuff. So this is a BPSK, right? This is a BPSK system. So, but this operation is not coherent like previous one. So it's not a direct BPSK system. So it's not. So not a direct BPSK system. What is that then? What we have to do? We have to do differential encoding. Then do the BPSK. The combination of these two is called DPSK, differential PSK. If it's a coherent system, then BPSK system is called BPSK system. If it's non-coherent system, BPSK system actually is called DPSK, differential PSK system. So let's see how the receiver looks like, because we know there will be an XOR signal. So this is the binary. So this is a receiver. Receiver. So binary sequence which we receive this signal. So there will be an XOR, means actually the delay will add here. This is called amplitude level shifter. What it do? This is an amplitude level shifter, which will do actually. It will actually make bit 0 to EB and bit 1 to minus EB. Then it actually do the traditional stuff or pulsing, which is actually our PT, pulse T equal to twice by T cos twice by UC. So this is this part. This part is the differential encoding. And this part is the typical BPSK receiver system. So we will see part by, because differential encoding comes new. So let's see what is that differential encoding, what it do actually, how its operation is done. Encoding. So what differential encoding do? For example, here this is DL. So it's delayed. It's got delayed. So this one will be delayed T. So this will be DL minus 1 bit delayed actually. Okay, so DL, how the differential function DL depends on. DL depends on this one A0. So A0 with XOR DL minus 1. So if you make DL minus 1 and A0 XOR, then this will be the output DL. That's actually the mathematical expression for this encoded operation. Now let us see how practically it happens. So differential coded bits are actually used to modulate the carrier with phase angle 0 and pi radians. So the differential coded bits are used to modulate or demodulate the carrier with phase angle 0 and pi radian. So here we will see some example. Our A0 is here. A0 DL minus 1 will be somewhere. L minus 1 and DL. Whatever is DL, L minus 1 will be the next bit, right? So here let's draw a scheme. So in your book, Sklar, there is an example is given. I took the same example. Okay, so it's actually 1 1 0 1 0 1 1 0 0 1. This is a bit stream. Okay, that is transmitted as A0. Okay. It can be any example. I'm just took the same example in your book. Okay, So A0. So DL for DL, you see, DL. For DL, we will assume a p-value that at any moment there was a value in DL, so that that value can come to be delay and can be added in the XOR. So you can assume actually any value. So for our like simplicity, we took the initial value of DL was 1. Okay. So if DL is 1, what will be the D minus L value? DL is the previous value, isn't it, guys? So this 1, you see, DL. If any more at second one, DL was 1. What will happen to the second 2? DL minus 1 will be that same value, isn't it? Same thing, DL. So next, what will be the DL minus 1 value? So this will be 1 here, isn't it? See, this 1 and 1 means A0, this 1 and that 1 which was here. This 1, so which is delayed, comes here. So that 1 is now here. So now 1 and 1. So what if it's the same value, 1 and 1? What will be the output? What will be the output if it's same value? 1 and 1? 0. If it's same, then 0 is different than 1. That's the XOR do. Right? So 1 and 1 will be 0, which is actually the next bit for DL minus 1. 0. So 1 and 0 is different. Right? So what will be the output? 1, which will be the next bit for DL minus 1. So again, 0 and 1 different will be 1. This 1 will be the next bit. 1. 1 and 1, 0. 0 goes. 0, 0. 0. 0 goes. 1 and 0, 1. So 1 goes. 1 and 1, 0. 0 goes. 0, 0. 0. 0 goes. 0, 0. 0. 0 goes. 0 and 1, 1. Right? So what will be the corresponding phase? We say there will be 0 and pi. So 1 will be, we have seen in BPSK, 1 is here, another one is here, right? So 0 and pi degree. So this is 0, this is for 1. So for 1, the phase is pi. For 0 is 0. For 1 is pi. Okay, let me write it in different color. So for 1 is pi. For 0, 0, pi, 0, 0, 0, pi degree. This is the corresponding values are transmitted, either 0 or pi in BPSK. So this is, for example, this is in your transmitter. For example, you receive the same stuff, pi, whatever, this same stuff, assuming you receive the same stuff. Now, how to decode it? How the BPSK, okay, just let me write it again. Then, okay. So you receive the same zeros, pi, 0, 0, pi, 0, 0, 0, pi. Now, you see, pi corresponds to what? Pi corresponds to 1, 0 corresponds to 0, 1, 1, 0, 0, 1, 0, 0, 0, 1. This is actually in your BPSK demodulator or whatever, detection. Now, what it do? Whatever the transmitter do, you see, for example, I say this is receiver. This can be your transmitter actually. This is a transmitter and receiver both. Whatever happens in the receiver is also happens in the transmitter. Now, in detection, 1 and 0 are the same or different? 1 and 0 are they same? No, they are different. So if it's different, then 1 and 0. 1 and 0. If they are different, then 1. Okay. If it's different, 1 and 0 different, then 1. 0 and 1 different, 1. 1 and 1 same, 0. 1 and 0 different, 1. 0 0 0 0 1 1 1 0 1 0 0 0 same, 0 0 same, 0 1 different, 1. Okay. So what was our transmitted bit? You see, this was our transmitted bit. And what is our receive bit? This is now our receive bit. You see, they are same. You see, 1 1 0 1 0 1 1 0 0 1 1 1 0 1 0 1. You see, it's same, eh? Same. So we actually receive the same bit. You see how we detect it? We transmit it. We do this operation, differential encoding, do the BPSK. We receive the same bit. So this is the transmission and reception works. Okay. So this is for our non-coherent BPSK system. So what is the probability of error? PB or PE, probability of error is, I'm not deriving the expression, you will do it. How? It's in your book, reference book, page. This is self-study. Very, very important. You will do it yourself. So this is for what? Which modulation scheme? This is for BPSK. Okay, so in our syllabus, we will actually look into two kind of BPSK. Sorry, two kind of coherent. One is a BPSK, another is a orthogonal. So our guys, any question regarding our previous one? Guys, question? No question? Okay. So our next scheme is a non-coherent orthogonal modulation. So non-coherent orthogonal modulation. So in non-coherent orthogonal modulation, we actually did some orthogonal in our coherent detection system. So we will actually study, like we will compare side by side. Okay, let's see. Let's consider a binary signaling system, binary signaling system or scheme. For that, we have a, for example, is common our common tradition equation xt. It can be expressed as 0 because it's binary. It can be expressed as 1. If it's 0, then let's give it a name, x1t. Say this is x2t. So a p1 t, because they are orthogonal. Here the main idea is orthogonality, means actually how will they differ? The differ will be this pt. So p here the P1, and we also have studied this, how the orthonormal, if we have two pulses, if these pulses are orthonormal. For example, minus infinity to plus infinity, P1t and P2t dt, what will be their value? Their value will be 0 because they are orthogonal. We have seen these properties in our which mechanism, guys? Where we have seen this? Where we have seen this mechanism? FSK. In our FSK system, our signal was orthonormal. So in orthogonal modulation, what will happen? At any symbol interval, either P1 or P2 will be transmitted. So at any symbol interval, either P1 or P2 is transmitted. So because this is non-coherent, what will happen? The received pulse P1, like received pulse P1 or P2, whatever, P1 or P2 will encounter with unknown phase shift. Encounter unknown phase shift. Theta will be added in the system. So if 0 is transmitted, what will happen? The received signal y, the yt will be a P1, which is actually our this one, ypt. Now it encounters another noise, the theta noise. Okay, of course channel noise can also be added. In general, we do not interested much about this noise because we have already characterized it many times. We never characterize the theta, that's why theta is more like in focus. So if one is received, one is transmitted, what will be the output, the received signal yt, a p2 t, and a theta, which is an unknown phase. This unknown phase theta, that is actually the main focus in non-coherent system. This N1 and N2, they are AWG and all these things. AWG and all the blah blah blah. We are not discussing it anymore. So what happens in a coherent system in FSK? This is an FSK system. Orthogonal is actually an FSK, means actually BFSK. So what happened in BFSK system? How we transmitted this? Let's compare. So coherent BFSK. So what's happened in coherent BFSK system? It was traditionally simple that yt, when we received a signal, we actually did it earlier, right? We have finished BFSK system, so we know how it works. So we down convert the system with two different S1 and S2 probably, then integrated it from 0 to t, then we have output as R1 t, for example, or R2t. Then they combine to form the R, because they are summed here to form the final RT, which will be sampled at T, which will be R capital T, then goes to a detection. Right? This is our typical BFSK system. Here actually this part, this is actually a correlator. Correlator is used when you have a knowledge of S1 and S2. You know it, what kind of frequency you are expecting. Here, remember what was our signal? Xt. Xt was same thing. This one. The transmitter is same. For transmitted signal is same for all scheme. AP1 T, AP2 T, which is actually A 2 by T cos twice by F1 T. Just recalling what happened in earlier cases. Cos twice by F2T, because this is frequency modulation. This frequency. So the frequency will be different. This F1 and F2, they are different. So this is used for bit 0 and it is for bit 1. Now, what happened to the will be in non-coherent system then? Non-coherent BPSK, or sorry, BFSK. In non-coherent system, this correlator cannot be used, because this correlator has to has a knowledge of previous carrier. So instead of that, we will use a match filter, because match filter is independent of modulation scheme. Match filter do not need any knowledge of previous things. It will just match to the transmitted pulse. It depends on the pulse, transmitted pulse. For example, it only look on this transmitted pulse, this part. It will only look on this transmitted pulse. So do not care. So how the non-coherent FSK receiver will look like for transmitted signal? Well, okay, this will be the same transmitted signal. The same signal. This will be the same transmitted signal. Okay, let me write it again. So for transmitted XT, for 0 and for 1, this will be the same. Twice EB by T cos twice by F1T and F2T. Of course, T is 0 to T. Same thing here. So how the non-coherent receiver will look like? Receiver will be matched filter. So our YT signal, when it will be received, now instead of correlator, we will be using a match filter. So this filter matched to pulse, the P1T, which is nothing but this part, this part. So which is actually P1T is nothing but square root 2 by T cos 2 by F1T. Same thing. So match filter. So filter match to P2. Of course, then signal will go to an envelope detector. Can anyone tell me what is an envelope detector? Guys, why do you used it earlier, envelope detector? Detector. Okay, so it will be sample.
For demodulation of what? AM signal?
AM signal, exactly. When we transmitted an AM signal, then actually we used a envelope detector. What envelope detector? You know the operation, right? So this is actually this part. I am not discussing it because this is part of your previous analog signal. That's why I'm not.
Sir, if you like, you could give a recap.
Sorry.
If you like, you could give a recap.
Okay, let's see how envelope. We are not going to Okay, so let me decision. So RT will be, you see, previous RT is greater than 0 will be 0, less than will be 1. Okay, so envelope detector. Envelope detector usually used in analog signal, right? So what happens in analog signal? So this is just for analog. We are not doing analog. We are much smarter. So we are doing digital. So what an envelope detector do? For example, you have a message signal, MT. So message signal have, for example, mm, this is the message signal, for example. Okay. Now you have a carrier signal, FC, the frequency of the carrier signal. What happened is this one. Like this. So what we do in transmission, you actually made multi or up convert the signal. So what happens? How the shapes comes then? So shapes comes like uh, mm, this way. Let me redraw it or yeah, drawing is quite okay. So now what will happen? For example, this is the axis, for example. Here is the after modulation. Here is this same, this one actually here comes the. So in modulation, what we to transmit? We transmit actually the carrier. Why we transmit the carrier? Because the frequency is higher. You see, this was our information, right? This is not information. This is just a carrier with higher frequency. So what we do, we modulate this amplitude of this carrier based on this guy. You see, this is shape, this one. Actually, this is not transmitted. You can remove it, just the shape. This is the how. This part is not transmitted. There is nothing here. Nothing here. So let me, if I redraw it, what will happen? Then it will be like, mm, you got it right, guys? How you see this is here actually the signal is. If you so what the detector do? Envelope. This is called envelope. The outer edge is called envelope. The detector tries to detect uh, the peak power, and it risk like replot it. By replotting, it actually detect the message from the carrier signal. We actually when in the demodulator, what we do, we actually remove this part, right? We remove this guy. For example, we technically remove this guy, and you see still my this envelope remains. You see envelope. So that's actually my message signal. You see message signal. So what you do in analog, you see this part, whatever in this part is actually this part, right? So you do not need to even transmit this part. So you actually remove, you can remove this part. That's what you call suppression. Carriers, you carrier suppress the carrier. You also suppress the one of the sideband, whatever the higher or the lower sideband, whatever. You see this one. Now, if I reconstruct it, this one, this is actually same thing as my this one, same signal. So this is how we detect the envelope. Envelope means actually the edge of that part. Got it, guys?
Yes, sir.
Okay. So this is actually how it do this stuff. Okay, so we have the match filter receiver. So this figure is the figure. So guys, from here we can understand that if any time you got confused that what should be my receiver, you can easily use a match filter. Match filter is like your last hope for any demodulation, because match filter, whenever you use a match filter do not looks for any modulation scheme or anything else. It only looks on the pulse. He wants to recreate the pulse, because by shaping its filter characteristics. Okay, so this is a match filter receiver of BFSK B or binary orthogonal. Okay, so last part. I'm just the same filter can be actually rewriting like this way. You will see in your, because that's also in your book. That's why I'm giving you this same idea. So this will be your down convert signal. Because you use match filter just now, right? So this is how the match filter will work. So envelope detector, so you will be do some squaring. And adding. Each two will be added. Each two will be added. Again, this two will be added, no problem. And this is your decision. So this signal will be this pulse 2 by t cos twice by f1 t. They will be square root of 2 by t sine twice by f1 t. Same thing, square root of t cos twice by f2 t square root 2 by t sine twice by f2 t. So this part, though we will be using a match filter, this part will now works as a like equivalent to a correlator of coherent system. Correlator. This is a squaring device. This is your like I and Q. So this is I and Q. So and then this is the decision. Okay. So the probability of error will be half exponential 2n0. Again, self-study. This is equation 4.96 in your book. Page. By this time you got matured, you know how to do these things. So this is your homework. Self-study, very, very important. Okay, so we are almost done. 1 or 2 minutes. Okay, so what we've done so far, we can do another one, just results. I will not derive anything detail. So how long is our class?
Sir, up to 45.
3:45.
We have
Okay.
4 minutes left.
Okay.
3 minutes left.
BASK, amplitude shifting, non-coherent. Same thing, XT twice EB by N0 cos 2 pi FCT for 0 bit. For 1 bit, nothing, 0. So in the receiver, same thing. In the receiver, you will receive the same signal, twice EB by N0 cos twice pi FCT. You see, we have a problem that we do not know theta, so theta is always added. Noise can also be added. We are not interested to this one. So this is for 0, for 1, for 1, nothing received. So you will receive only noise, nothing else. So how the receiver look like? YT, same thing. This is only one branch. So filter, match filter, filter, match to this part. twice pi fc t plus theta. Go to the envelope detector. And then decision, like sampling and decision. Now, what is the probability? Probability is half. They have the similar expression, minus EB by 4n0. You see, it's EB by 4n0. Previously, it was EB by, what was our previous one? 1n0. Next one, what is that? 2n0. Now it's 4n0. So if I plot probability of error here and EB by n0, what will happen? This BASK, our new model BASK, it having the lowest because it's divided by 4. You see, it has the lowest, means it has the better performance, BASK. Then the 2, this is divided by 2, so this is for which modulation scheme? FSK. So B FSK, and the worst one was the previous one, DPSK. This is the way the performance will look like. Okay, guys, I'm on time. Let's stop the recording. Okay, Siar,
Yes,
can
sir.
we have our next quiz on the Friday? This
Sir,
Friday?
on 6, on 5, we have already another quiz on 6. To have a
On
quiz in such a short notice might be really difficult, sir. We will be
okay,
talking between ourselves and deciding the date, inshallah, sir.
okay. Let me
Sorry,
know.
sir.
Let me know.
Okay, sir,
Okay.
inshallah. Salam
Thank you
alaikum.
then. Thanks, sir.